Hey everyone, great to be here. My name is Martijn Visser. I'm a senior product manager at Confluent. I joined Confluent in the beginning of the year when the acquisition of Immerok took place. I was working at Immerok, the Flink startup back then, working on Flink here at Confluent. Next to being a senior product manager, I'm also a committer and a PMC for the Apache Flink project. And today I'm here to talk about getting data in and out of Flink. And hopefully at the end of this talk, you will have a better understanding of Flink and its connector ecosystem. So customers and companies are becoming more and more digital, and the amount of available data is growing every day. Customers' expectations have changed, and real-time services have become the standard. Now there's all sorts of real data examples. Could be your latest retail order of your latest pair of shoes, getting a notification or getting the information about it's being shipped out, using the mobile app of your favorite streaming service. All of that data could be used in a real-time stream processing solution. And Flink is a framework that makes it easy to process streaming data in real time. And when we're talking about processing, it refers to manipulation and transformation of data into a more useful form. Common examples are cleaning or filtering of data, transforming it into different formats, or structures, and performing calculations or aggregations on top of that. And with stream processing, you're analyzing data in real time, so you have the immediate reaction and insights. And all of these real-time stream processing solutions are used to create stuff like rich front-end customer experience and real-time back-end operations. So Flink offers multiple ways of defining the business logic that is needed for powering these customer experiences and back-end operations. These APIs are designed to cater to different use cases and level of expertise, and it allows you as a developer to choose the appropriate level of abstraction for your use cases, and it helps you building these efficient and scalable stream processing applications. So on the top part, at the most declarative option, you have Flink SQL. It's a 100% SQL-based solution where you're only using SQL to basically query dynamic tables, which is your sources and your sinks, and you're expressing all of your business logic in SQL itself. One level lower is Flink's table API, which you can compare to being the programmatic equivalent of SQL. So instead of using SQL, you use Java or Python to actually have, in a declarative way, define that business logic. You can also mix and match table API, and you can mix and match SQL in there as well. One level lower is Flink's DataStream API. It's a low-level imperative API, and it exposes building blocks for stream processing, such as state and timers. And the lowest level, you have a process function, and that is for fine-grained processing of individual elements. And your Flink job runs on Flink's runtime, which is a unified runtime that can handle both batch and streaming applications. As you can see, the DataStream API directly runs on top of the stream operator API, which is executed in the runtime. With a table API or a SQL application, it actually goes into a validation, an optimization, and a planning step before actually being executed on that runtime. Now, a stream is nothing more than a sequence of events, and all business data is always a stream. Bounded and unbounded refer to the characteristics of the streams that you want to process. It's basically if you know or don't know if that stream will end. And Flink treats batch processing as a special case in its runtime. Batch execution is only applicable to bounded streams. That's because it exploits the fact that it can process the data all in one batch rather than event by event. And possibly execute different batches after one another, of course. With streaming execution, you run everything at the same time, so you are continuously processing events or small groups of events. You can use streaming execution on a bounded stream, it's just not as efficient. Now, the Flink community has always believed that it should be possible to have a runtime that is state-of-the-art for both stream processing and batch processing use cases at the same time. A runtime that is streaming first, but it can exploit just the right amount of special properties of bounded streams to be as fast for batch use cases as dedicated batch processors. Flink has one unified API for both batch and stream processing, as you have seen with the different options that are out there. There are two main reasons for that. It's all about reusability as the first one. So you can have efficient batch and stream processing under the same API, and they allow you to switch between the different execution modes without actually rewriting your code. So a job could be easily reused to process historical data, but also real-time data. And there's an operational simplicity involved as well. If you have one unified API, we only need one single set of connectors. You can have one single code base. And you can also have, let's say, efficient implementation of things like mixed execution pipelines for use cases such as backfilling. Now, as a result, developers don't have to learn multiple APIs while still having consistent semantics across both batch and stream processing. And for connectors, there's one connector stack for both bounded and unbounded streams, depending, of course, on the system that you want to connect to, because it doesn't make always sense for the system to actually have a continuous or a bounded or an unbounded mode. So in order to use Flink, you have to get data in and out of the system. Flink by itself is not tied to any connector itself. So you can use it to read and write files. You can connect it to distributed log systems like Kafka or Kinesis or Pulsar. But you can also connect to databases via JDBC or key value stores. Basically any other system. And connectors need to work with Flink's fault tolerance model. If you don't properly integrate your source with Flink, it means that you could lose some data if a failure actually is occurring. When a failure occurs, Flink uses a so-called checkpointing mechanism or a snapshot mechanism to recover from that. But in case you have written a bad connector, you could actually end up in a situation where you have not processed some of the data. Another consequence, of course, of going back to an earlier checkpoint or an earlier snapshot for recovery purposes is that you could reprocess some of the messages that you had already processed earlier. So if you have a situation like that, you could end up with duplicate messages. This is an overview, let's say, of the state of Apache Flink connectors. On the left-hand side, you see the connectors that are currently part of the Flink project itself. So we're looking at Kafka, Cassandra, MongoDB, Elastic, different AWS with Kinesis and Firehose, OpenSearch, JDBC, Pulsar, HBase, a lot of stuff. On the right side, in the square bracket, you see some of the connectors that are also available from a Flink, or as a Flink connector, but they are not part of the official Flink project itself. One of the most popular connectors out there that is not part of the Flink ecosystem or from the Flink project itself are the CDC connectors, which allow you to perform change data capture streams by directly connecting it to databases like MySQL, Postgres, Oracle, Microsoft SQL Service, etc. But there's also direct integration with technologies like Iceberg, Paymon, Hoodie, Delta Lake, ClickHouse. There's a Pinot connector, HTTP. There's a wide variety of connectors available that you could use for actually connecting in Flink. In order to understand how sources and sinks work in Flink, I also need to explain a little bit of how Flink works under the hood. So if you are writing, let's say in this example, a Flink SQL statement, you end up with a job graph. And a job graph or a topology is basically the set of different operations that is happening in the application in order to do the processing as your business logic is dictating. So in this example, we are inserting into a table which we call results, and we're reading from a table called events. So in this case, as you can see, is that the events are at the beginning and they are part of that job graph, as is the same situation for the results. Now that I've explained a little bit about Flink, I have to say I took a little bit of a shortcut in some of the ways, but it's in order to make sure that we're also having enough time to actually talk about the Flink different interfaces to write your connector. And further stuff, I'm going to start with Flink's source interfaces. So on a lowest level, there's a unified source interface. It has existed since Flink.1.11, and it's been annotated as public since 1.14, meaning that the API is stable since 1.14, it's roughly 2 years ago. And the source component in Flink has 3 core components in there. There's a component of splits, a split enumerator, and a source reader. Splits are portions of data that can be consumed by the source. An example of a split could be something like a file, either the file itself, or perhaps you have a file format like Parquet that allows you for actually splitting that file efficiently, or something like a log partition in case of a Kafka. Splits are the granularity by which the source distributes the work and parallelizes reading the actual data. So it is a compositional API. You have a source, which is basically a factory or a configuration holder, and only that interface is being serialized and being shipped to the job manager and the task manager. The job manager is the central component that takes care of the orchestration of the entire Flink application, and the task manager are basically the machines that are executing the work that is being parallelized. Now, the source component is used to create one split enumerator per job, and that split enumerator runs as a single instance on the job manager. It does things like split discovery, split lifecycle management, failover, and split reassignment. You could also say that it maintains the backlogs of all pending splits, and it assigns them to the readers in a balanced manner. Now, the source reader component that actually requests the splits and processes them, for example, by reading the actual file or the log partition that is represented by that split. The source readers are run in parallel on the task managers in the source operators, and they produce the actual parallel stream of events and records that flow through that job graph at the beginning. In this entire interface, there's a lot of things that have been abstracted away. You don't need to worry about stuff like a threading model, fault tolerance, and cancellation, as long as you implement the right interfaces and methods that are available from a Flink point of view. There's also a higher level source abstraction, which is called source reader base. Source reader base is an abstract implementation of the source reader, and that you can use for long-living splits that you want to track continuously. It basically means that you are continuously pulling the splits rather than being notified and sending requests whenever a new record is coming in between the enumerator and the source reader. And with the source reader base, the idea is that developers can write their own source and just focus on fetching the records, parsing them, extracting timestamps, and potentially dealing with things like watermarks, which we'll talk about in a few minutes. It allows for easier implementation for custom sources in Flink. And if you're using the source reader base, the source reader can maintain state about the progress of each split that it's reading, which is particularly useful if you have long-living splits that need to be continuously pulled. And overall, the idea is that it can really simplify the implementation of any custom source in Flink, because you only have to focus on the core functionality of fetching and processing records. You don't have to worry about stuff like split tracking, state management at all. And in the end, this is the recommended way to actually implement a source connector. So now that you have a basic idea of the source interface in Flink, let's have a brief understanding of how the sync interfaces actually look and what options you have in here. So the unified sync interface actually follows a similar path to the source interface. It is also a compositional API. It exists since Flink 1.12, and it's currently partially in public evolving and in experimental. Public evolving in the Flink terminology means that the API can be broken between minor versions, and experimental means that it can be broken between different patch versions of the applications. So this is not a fully yet settled interface, but this is something that the community is working on quite hard. So again, this is a compositional API, and it consists of several elements. So you have a sync, which again, same as with the source, it's a factory, it's the only serializable interface that you have. Then next up, you have the sync writer, which actually takes care of writing that information for you. And then there are a couple of options that you have in there that you could do in there. There's a pre-commit topology, which comes then after the writing. A pre-commit topology is a way to insert custom logic or hooks into the sync before the data is actually being committed. So you could basically do additional processing or transformation of the data before it's made visible. A good example of that would be, for example, in case of a Hive connector, where you would like to do a compaction of different small files into a larger file before that actually making available. But in the case of Hive, Hive itself does not support updates. So it means that once a file is written to Hive, it cannot be updated, it can only be appended. By using a pre-commit topology, you could have that custom logic that actually compacts the file before it's being made visible in the metastore itself. So it's a way of basically improving your output from the system. The committer is a necessity in case you want to enable two-phase commit protocols or transactions, and it enables exactly one's syncs. So this is quite commonly used in the Apache Kafka connector and Pulsar and everything else. What happens is that the sync writer writes the data to the disk, and it creates so-called committables. And these committables store the data of the current, or store the current state of what has been written so far. And these committables are then passed on into the sync committer, and that is which is made responsible for ensuring that the data is committed and made visible whenever a checkpoint is made in Flink. Now, the sync committer must ensure that the data is properly committed and made available for in case of a failure or a restart. By doing that, Flink can guarantee that the data is consistent and durable, even in case of a failure or other issues. The last part is a post-commit topology. This is again quite a common example for doing some additional processing after the data has actually been made visible and available. This could be useful in the case of an iceberg connector, which actually writes the files immediately to the sync and use a post-commit topology to take care of compaction after they have written the files and updating their file logs. Because unlike Hive, it can actually deal with these type of transformations. So in these specific interfaces, on a public evolving level, we're looking at the sync writer and the committer. Those are, let's say, elements that have been available and being used in Flink for quite some time. And the pre-commit topology and the post-commit topology are currently experimental and being worked on to promote them to a full, flexible, and stable API. Now, with next up, I want to talk briefly about batch, actually. There is an implicit support for streaming and batch when you're creating a connector, for a sync connector. If you're doing a source, you need to have some sort of configuration flag that indicates if the source is actually a bounded or an unbounded stream. But in case of a sync, that is not the case. It's abstracted away. That is because it's handled by Flink, and it's based on the execution mode of your Flink job itself. So when your job is in streaming mode, everything is committed on checkpoints. If committables are failing, they will be retried in the next checkpoint, potentially infinite until it actually succeeds. Those retries only are in case their failure is asynchronous, like a remote procedure call that's failing between a task manager and a job manager. If there's actually something happening like a synchronization failure, like a flushing, that would fail the checkpoint, of course. And depending on the configuration of your Flink job, that could also fail and restart your entire Flink job, and it would go back to a previously made snapshot that actually works. And when the job recovers, it will recommit all the committables in the last checkpoint. If your job is in batch mode, everything is just committed when all the data has been processed. There are no such thing as checkpoints in batch mode. All data is written in one last transaction, and we only commit when everything has been completed. Next to these interfaces, the recommended way for actually building your sync is to use the async sync. So Flink has several syncs that all have a similar functionality, but they are all developed and maintained independently. All of these syncs do stuff like batching events, signing requests, sending them to the respective endpoint, retry or throttle requests, and they participate in checkpoints, of course. Now, async is a base implementation for asynchronous sync. And you should really use it in case you need to implement a sync that doesn't require transactional capabilities. Adding support for a destination or sync only requires a lightweight shim that implements the specific interface of the destination using a client that supports asynchronous requests. So the responsibility for you as a developer is you have to convert your input you convert your input to a request. The async sync bundles those into batches. You send out those batches asynchronously, and in case there's any failure, the async sync will actually resubmit those failures. And the async sync has, let's say, a convenient way of batching those things. You can configure them to either be size-based, so when you have X amount of requests or Y amount of bytes that have been reached, but you can also have a time-based batching, so every Z seconds, of course. And whichever triggers comes first, it will do the firing of the thing. So the async sync is designed to participate in checkpointing and provide at least one semantics. It is, of course, limited to destinations that provide a client that supports asynchronous requests. And again, in the async sync, it abstracts things away like a threading model and has a log-free implementation. Now, what if you don't want to write a sync? Could be. One way that I've seen people in the community do it is actually they leverage the async I/O capabilities. So async I/O is an API in Flink, and it's purposely meant for doing enrichment or lookup streams. So you would have something like flowing data in from Kafka, and you would do a call to an external database to enrich that stream. But if you're going to make a call to an external system, you could use it as a sync. It's not a recommendation, but if you really don't want to use this is probably the most easy way to get it done. Still, with this entire thing, you would have only at least once guarantees. And the async API handles integration with data streams, handling orders, event time, fault tolerance, retry support, etc. I want to talk also about two important connector capabilities. So if you have built your source or your source connector, because I think I have specifically looking at two different source capabilities, that you would get out of the box if you would actually build your source using Flink's source interfaces. First off, there's the hybrid source. The hybrid source is a special type of source which powers use cases to enable initial loads or backfills by reading from one or more bounded sources before switching to an unbounded sources. So an example would be is that you have a bunch of historical data stored on S3 in Parquet files, which might be coming in from Kafka, and you have a data pipeline that you want to start using that data. And at first, you would actually read all that data from Parquet on S3. And at some point, you would actually seamlessly want to switch that over to an unbounded source, being Kafka, for example. So the hybrid source enables you to switch from sources either with predetermined start positions, or you can do a position conversion at switch time. And the hybrid source itself can be used with any source that's using the unified source interface. All right. Another thing that I want to mention is watermark alignment and idleness detection. And in order to properly explain this, I need to do a little bit of a side tour to actually explain what watermarks are. Flink on its own does not have a concept of time at all. And it uses watermarks to actually measure the progress of event time. Event time meaning there's something in the payload of the data that indicates when the event actually has happened. And a watermark is an assertion about the completeness of the stream. And if you look at the diagram, you start on the right, you see that there's an event coming in. It has a time of 7. The next one that is coming in is 11. You have 15, 9, 12. You see that it's not properly ordered from that matter. That's because this stream is out of order. Now, a watermark is the maximum timestamp that has been seen so far, minus an out-of-orderness estimate. So you can say how much out of order the data is allowed to be. Now, why is this useful? What you see quite often when you're reading from a source and you're using event time processing is that some of the splits, like a partition or a shard, actually has more events that have a specific event time that is too far ahead of the rest. And what you can have in such a situation is that you're actually ending up with skew in your job processing graph. By having watermark alignment, Flink will actually do won't increase the watermark too far ahead to actually prevent that skew and have an efficient processing in your application. Another thing can also actually happen. If you have idleness detection, you could have a situation where Flink is basically not progressing the watermark anymore because there's no data coming in. But if you have a proper way of detecting idleness, you can mark a source, or split, or shard, or a partition as idle. And that will actually help Flink progress or mark that watermark as being progressive. And that is important because watermarks are basically at the heart of most of the stream processing in Flink. It's used for determining when a window needs to be opened and when it needs to be closed. It's used for all sorts of aggregations. It's one of the key elements if you want to do most of the computations in Flink. We're going to the end of the presentation, and I want to talk a little bit about the current state and also talk about contributions. So I've been extensively and only talking about the unified source interface and the unified sink interface. But Flink also has what we call a source function and a sink function. And they have been around since before Flink 1.0. Now, most of the important connectors have already been migrated off of the old interfaces. But why is that actually? Well, that's because these interfaces were only meant for streaming. They are rather monolithic APIs, and they have all sorts of issues like serializable with non-serializable fields in there. If you're building a source on a source function, you get into situations where you have to do push-based, making checkpointing really inconsistent when you are encountering a situation of back pressure. You have to take care of all sorts of stuff like split discovery, data deserialization, animation, and offset management. Taking into account stuff like thread synchronization, cancellation. And you can also have the situation where chain tasks run in the source thread. For sinks, it's slightly better, but you still run into issues with stuff like data serialization, animation, and transaction management. And it's actually quite hard to write an exactly one sink in using the sink function. Asynchronous callbacks are quite complex to handle, and usually involves synchronization within the sink function. So the source function has already been officially deprecated, and we're planning to remove that in Flink 2.0. And there's currently a lot of work going on to actually get the unified sink interface into a state where it's completely finished and ready, so that we can also fully deprecate the sink function. With the goal that I think I have as a personal goal is that we end up with a Flink 2.0, which is something that Flink community is currently discussing probably somewhere next year, where we would no longer have the source function and sink function, but of course it depends on how things are progressing. But that is the goal. So what if you are interested in actually contributing to Flink connectors? There's a couple of things that are good to know. So since the last couple of Flink releases, I think it's roughly been a year ago, all the Flink connectors itself have been externalized from the Flink repository. Usually they were always bundled and every connector release was tied to an actual Flink release. But that is no longer the case. So for example, the Flink Kafka connector resides in a Flink connector Kafka repository. The AWS connectors reside in their own repository itself. There's a number of reasons for that, but the idea is predominantly to force Flink community to stabilize their source and sink interfaces, because we want to make sure that users can reliably get data in and out of the system. But it also allows for connectors to be made compatible with different versions of Flink. So if we're introducing a new version of a new feature in a connector, like rec assignment in the Kafka connector, it won't be made available only in a new Flink release, but we could also backport that rather easily towards older Flink releases as well. Now, in general, the Flink community loves contributions to connectors. The easiest and most obvious one is you build your own, and there's a dedicated flinkpackages.org website where you can link and host them. You can find there not only connectors, but also other elements like metric reporters and a bunch of other extensions that have been made on top of Flink. If you're interested in actually building a connector for as part of the Flink project, I would recommend that check the Jira project Jira project, see if there was already a tick about it, or open a discussion in the dev mailing list. I would love to recommend, or not only recommend, I would basically try to persuade you to help out with this. We do have some situations where connectors are actually lacking maintainers in general. An example is RabbitMQ, Google pops up in Elasticsearch. It's some of those connectors that have not yet been ported to the new interface. If you are interested in contributing any connector in any way, but you feel like you're stuck or you don't know where to go to, feel free to reach out to me. I'm more than happy to see if I can somehow help you and get organized in this way. And with that, I would like to thank you for your attention.